Yeah, okay, so it's 4 5. Let's start. I'll share my screen. Is my screen visible? Yeah, so is my screen visible? Okay, yeah, then I think we can start. So first let's recall what we saw then this week. So this week we saw the definition of the complexity class PP. So PP is the class of all languages L such that there exists a probabilistic Turing machine M. Just a second, someone wants to join. Yeah. Yeah, so PP is a class of all languages L such that there exists a probabilistic Turing machine M satisfying X is in L implies probability that M outputs 1 is at least half. Again, someone wants to join. Yeah. And probability that, okay, so if X is in L, then the probability that MX outputs 1 is at least half. And if X is not in L, then probability that MX outputs 1 is strictly less than half. So if I were to add a small inverse polyfactor over here and subtract a small inverse polyfactor over here, then this would be very similar to, this would exactly be the definition of the class BPP. The difference over here is that there is no like additive factor, no inverse polyadditive factor over here. That is, there is no gap between these two probabilities. And even though that might seem like a minor difference, that is a huge difference. It makes a, yeah, yeah. So because of that, proving some statements about PPR is really difficult, and that also makes PP very powerful. So it is known that RP, co-RP and BPP are in PP. So it's easy to see that RP and BPP are in PP. As far as co-RP is concerned, it's in BPP because RP is in BPP and PP is closed under complements, under taking complements. However, like it was easy to see that BPP is closed under taking complements, but to show that PP is closed under taking complements is not that easy. In fact, it was an open problem for like 14 years until someone solved it in, I think, mid 1990s. Yeah, and uh, unlike BPP, so we don't know if BPP, we don't know the relationship between BPP and like, okay, so we don't know that whether NP is contained in BPP or not, but over here we know that NP is contained in PP. Yeah. Then you saw the Sipser-Gax theorem, which relates the BPP with the polynomial time hierarchy. So it says that BPP is an intersection of sigma 2 and pi 2. And then you saw something about circuit complexity. Yeah, so that was all for the recall. So if there are no questions about this, we can start with the problems. Okay, so let's move on to the problems. So the first problem is the following. Suppose we want to boost the probability of success of an RP algorithm. Which of the following is the desired approach? Run the algorithm multiple times and accept if and only if at least one of the iterations leads to accept. Run the algorithm multiple times, except if and only if all of the iterations lead to accept. Run the algorithm multiple times, except if and only if an odd number of iterations lead to accept. Run the algorithm multiple times, except if and only if a majority of iterations lead to accept and there is no clear way to boost the probability of success. So what's the answer to this question? Okay, so if no one wants to guess, the answer is A, and we can, so what we should do is we should run the algorithm multiple times and except if and only if at least one of the iterations leads to except. How many times should we run the algorithm? That depends on like what probability of success do we want. So let's quickly see why this is the case. So yeah, so suppose that language L is in RP. So what does this mean? This means that there exists polytime probabilistic Turing machine M such that X is in L implies probability Mx is equal to 1. This is at least half, and X not in L implies probability Mx is equal to 1 is 0. And let M prime be a machine that repeats or executes M t many times. Also let xi be the random variable, which is 1 if mx is equal to 1 during the ith iteration, and 0 if mx is equal to 0 during the ith iteration. Okay, so and also yeah, let yeah, so now okay, if x is not so if x is not in L, then xi is equal to 0. Okay, let me write it like yeah, xi is equal to 0 for all I in t, because if x is not in L, then m is never going to output 1, and therefore xi will be 0 always. So in this case, m prime, since m prime repeats m and only outputs 1 if m outputs 1 at least one time, m prime would also output 0, and so this implies that m prime x is equal to 0, and so the second condition is fine for m prime. For the first condition, x is in L, then this is what we want to lower bound, probability m prime x is equal to 0. This is equal to the probability that x1 is equal to 0 and x and x2 is equal to 0 and so on, and xt is equal to 0. Okay, now what I'm claiming is this is equal to product I in t probability that xi is equal to 0. Okay, so why can I write this probability as this probability? It's because
Dependent
yeah.
random variable.
Can you repeat that?
Independent random variable.
Right. Yes. So the different runs of the algorithm or m prime are independent. So we get this. And okay, so what do we know about probability xi is equal to 0? So xi is equal to 0 means that mx is equal to 0, but x is in L, so probability that mx equals to 0 is at most half. So this is 1 over 2. This quantity is 1 over 2 to the power t. Therefore, probability m prime x is equal to 1. This is at least 1 minus 1 over 2 to the t. And now using this you can figure out what t you want. So if you want the probability to be, let's say, exponentially close to 1, t equals n would work. And in that case, the blow up in the running time would be at most by a multiplicative factor of n, so the algorithm would still be polynomial time. So is this fine?
Can you repeat that last sentence again?
Okay, yeah. So suppose you want the error to be at most inverse exponential. So suppose that means that suppose you want 1 over t, 2 to the t to be at most inverse exponential, that is 2 to the t to be exponential. Okay, then t is equal to n is fine, right? And what does t equals to n mean? T equals to n means that m prime repeats m n number of times, right? So if the running time of let's say the running time of m was n square, then the running time of m prime would be n cube. So if the running time of m was polynomial in n, then the running time of m prime would also be polynomial in n, right?
Oh, right. Okay.
Yeah. So basically this is why we like don't care about this exact constant in the definition of RP. I mean, even if it were like even if it were, let's say, 1 over poly n, we could use the exact same argument to bring it up to 1 over half. But that's not what we are doing over here. Yeah, here we are just boosting the probability, the success probability.
Right.
Yeah.
Okay.
Yes, the next problem is sort of complementary. It's for co-RP. So suppose we want to boost the probability of success of a co-RP algorithm. Which of the following is the desired approach? A. Run the algorithm multiple times and accept if and only if at least one of the iterations leads to accept. Run the algorithm multiple times except if and only if all the iterations lead to accept. Run the algorithm multiple times except if and only if an odd number of iterations leads to accept. Run the algorithm multiple times and accept if and only if a majority of iterations lead to accept, and there is no clear way to boost the probability of success. So this one is very similar to the previous one. So would you like to venture a guess?
See, I just want to say B probably.
Yeah, so that's the correct answer. Like one way to do it is to just repeat the previous argument, but replace, okay, let's go to the previous argument. So one way to do it is just repeat this argument, but replace this thing over here by the definition of co-RP and carry on with the argument. You would get the result. Another way to see this is the following. So there is this sort of duality between RP and co-RP, right? So the definition of RP, you have x in L implies probability of mx equals to mx equals to 1 is at least half. The probability of co-RP, in the definition of co-RP, what you can say is x is in L implies probability mx is equal to 0 is 0. So basically you can sort of switch these two statements and replace this one with 0. So basically what I want to say is whatever role 1 plays in the definition of RP, the same role 0 plays in the definition of co-RP. So all you need to do is, instead of worrying about what's probability of xi being 0, just worry about what is the probability of xi being 1. And that sort of almost immediately gives you that B is correct. Yeah. So we won't solve this because it's very similar to the previous problem. But you can try this on your own. If you have a problem or you can't do it, you can either ask in the forum or ask me in the next session. Yeah, so if that's fine, let's move on to the third problem. So the third problem is the following. Suppose we want to boost the probability of success of a BPP algorithm. Which of the following is a desired approach? The options are the same. Run the algorithm multiple times, except if and only if at least one of the iterations leads to accept. Run the algorithm multiple times, except if and only if all of the iterations lead to accept. Run the algorithm multiple times, except if and only if an odd number of iterations leads to accept. Run the algorithm multiple times, except if and only if a majority of iterations leads to accept. And run, there is no clear way to boost the probability of success. So would you like to guess this one?
I think in the lectures we use the majority function.
Right, yeah, okay. So that's the answer. And like, okay, we'll work this out. But can you tell me an intuitive reason why you need majority? Okay, okay, or rather, let me ask you this question. Can you tell me why for RP and co-RP we did not need majority?
Because both are one-sided there.
Right, yes. So that's the reason. Over here, like, so okay, suppose you run an RP algorithm multiple times. If it outputs 1, you are sure that X is in the language. But if you run an BPP algorithm multiple times and it outputs 1, it might be wrong. So yeah, you can't just
Right.
say if it outputs 1, at least once will accept, and if it outputs 1 all the time only, then we would accept. You have to do something in between. And majority is exactly that. So let's see why this is the
Why
case.
can't we do that odd number like the option C? Like,
Okay, so okay, I can okay. So when we do the analysis, it would be clear why we need majority. But here's a like sort of an intuitive answer why an odd number of iterations is a bad idea. Okay, so odd and it so that depends on the so odd and even is a number of parity of the algorithm. Sorry, is a parity of a number, right? And that's on a very stable quantity, right? So for example, you run a
yeah.
let's say you have one random process, you run it multiple times.
Right.
Like you can't say something like okay, if I run it like if I run it so in the first in the first batch of iterations, if it outputs an odd number, you can't say that in the second iteration it would also output an odd number, right? What you can say is the numbers outputted in like sort of different batches of multiple runs would be close to each other, right?
Right.
Yeah.
Okay.
So for example, if you toss a coin 100 times, you might get 51 tails. You toss a coin 100 times again, you might get 50 or 52 tails, right? You would get a number that's
Right.
close by, no, but not necessarily of the same parity.
Yes. Oh, no, but my question is like, why was majority function used? And there could have been okay. Maybe you'll
Okay, so
proceed.
right. So why exactly the majority use
Maybe there is
that?
another function that we could use.
Right.
That
Okay.
is what
So
I want to ask.
yeah, you're probably right. We can use some another function other
Right.
than majority, but
Yeah.
we can at least argue it's none of these three, right?
Ah. Right. Okay.
Right. And why we need majority, that we'll see in the analysis. Or sorry, why we can use majority is what we'll see in the analysis, because the analysis
Right.
I'm going to
Sure.
do is just one way of doing it, right? If you do it the other way,
Right.
probably some other function would work.
Yeah. Okay.
Yeah. Okay, so let's say, so suppose L is in BPP. So what does this mean? This means that there exists a polytime probabilistic Turing machine M such that if X is in L, then probability mx is equal to 1. This is at least 2/3, and x not in L implies probability mx is equal to 1. This is at most 1. So this is just a definition of BPP. So let again m prime be the Tm. This is m prime would also be probabilistic, so I could write PTM that repeats m t many times again. I would define xi in a similar way. Xi okay, for all I in t, let xi be the random variable that is 1 if mx is equal to 0 in the ith iteration or in the ith repetition, and 0 if mx is equal to 0 in the ith iteration. Okay, and now we'll define one more variable. Let x be sum over I in 1 to t xi. Okay, so can you tell me what x represents? So xi represents the output of m on x in the ith iteration. So what does x represent? Okay, so how many, okay, so x is a sum of xi's, right? So and xi's are 0 1 random variables. So this sum is going to be exactly equal to the number of xi's that is 1, right? Is that okay?
Yes.
Yeah. So then can you tell me what x represents?
Total number of times m has accepted x.
Right, exactly. And so what are we interested in? We are interested in the probability of x being in a certain range, right? X being small or x being large, depending on whether x is in L or x is not. Yeah, depending on whether small x is in L or small x is not in L, right?
Right.
Yeah. So let's do one case first. Yeah. So suppose, yeah, there is x, small x is in L. Then for all I in t, what is this probability? This is at least 2/3, right?
Yes.
So for all I in t, this quantity, the expected value of xi, this is just 0 times probability xi is equal to 0 plus 1 times probability xi is equal to 1. This is just probability xi equals to 1 because this is multiplied by 0. This is at least this is at least 2/3, right?
Yes.
Yeah, so what does this tell us? Now we are ultimately interested in x, so let's look at this quantity. So this is expected value of sum I in 1 to t xi. Now can you tell me what I should do after this? I have expected value of xi's. I want the expected value of x. How should I get this?
Summation over I to t expected value of x.
Right. And what is this called?
Additivity of
Yeah,
expectation.
additivity of expectation or linearity of expectation.
Right.
Sum over I in 1 to t. expected value of xi. So this is at least 2 over 3 times t, right? Because each one of these is at least 2 over 3, and there are t many of these. Okay, so we found expected value of xi x, but why did we do this? Well, the reason we want this is we'll use something called Chernoff bound for this. So have you seen Chernoff bounds in class?
Yes, it was defined, but
Yeah.
I did not understand it properly though.
Okay, yeah. So here's what the Chernoff bound says in this one direction. So it okay. So okay, let me write the exact statement. Dependent 0 1 random variables. Any delta greater than 0 probability that the absolute value, oh, I'm using y, not x. Probability the absolute value of y minus its expected value is greater than or equals to delta times its expected value. This quantity is upper bounded by e to the minus delta square expected value of y over 3. So what this is saying is the following. So okay, you might have heard this a lot. Suppose you toss a coin a few times, let's say 100 times. Oh, okay, 100 is a small number. Let's say you toss a coin a million times, and so how many tails or how many heads would you expect? You would expect about half of them to be heads, about half of them to be tails, right? So you would expect, let's say, about 500,000 to be heads, 500,000 to be tails. Chernoff bound just formalizes this. So what it says is that, okay, so over here the number 500,000 is the expected number of heads, right? Or the expected number of tails, right? If the coin is fair.
Yeah.
So what Chernoff bound says is that it just formalizes this. So what it says is that with very high probability, you won't be too far away from the expectation. So for example, in the when you toss a coin a million times, y would be the total number of coins, sorry, total number of heads. Expected value of y would be 500,000, and delta can be anything you want. So let's say you want to find out what's the probability that the number of heads is between 500,000 plus or minus say 50,000. In that case, delta would be 0.1. Is this fine?
Plus or minus what?
Okay, so suppose you want to find out what is the probability that the number of heads would be between 500,000 plus or minus 50,000. So so it is between 450,000 and 550,000.
Right.
Right.
Okay.
So in that case, delta would be 0.1 because 50,000 is like 500,000 divided by 10.
Right.
Yeah.
Right.
Okay, so this is the Chernoff bound, and we'll use this in this to prove that the success probability is pretty large, and
Right. Okay.
our y in this case would be x, and notice that x is a sum of independent 0 1 random variables. So it
Right.
does
Yes.
satisfy the hypothesis. We can use Chernoff bounds for x. Okay.
Right.
Yeah.
Yes.
So what do Chernoff bounds give us for x? So they give us that probability. Okay, so what are we interested in? What probability do we want to upper bound? The probability that we want to upper bound is this, right? Because x is in the language, and recall what we were going to do. We were going to accept, if and only if at least half of the iterations accepted, right? So we want to say that with very high probability, at least half of the iterations would accept. That is, with very high probability, at most half of the iteration, sorry, less than half of the iterations would reject x. So probability x is less than equals to t over 2. This is what we want to upper bound, right? Is this fine?
Yes.
Yeah. Okay. So this might look a little different from this, but yeah, what you can do over here is you can remove this absolute value. You would get probability. Okay, so if you remove the absolute value, you would get something like probability y minus expected value of y is greater than equals to minus delta times minus this and less than equals to minus this, right? Okay, yeah. Before this, it's better if I just write this in the exact form that I want. Yeah, so this implies that probability. Oh wait, there is a 2 over here because I'm using absolute value, so there is a 2 over here. But yeah, we don't need to worry about that. So probability y is less than or equals to 1 plus delta times expected value of y is less than or equals to e to the minus delta square x y over 3. Now, okay, this is strictly speaking not an implication because I should add a 2 over here, but yeah. So another way to write Chernoff bound is this. Wait. Yeah. No, wait, no, there is a mistake. Yeah, it's the other way around. Yeah. Yeah, so this is the form that we would use. So we have this. We want to upper bound this probability. So first of all, what we should try to do is we should try to write t as 1 plus delta times expected value of t. Should find delta such that 1 minus delta times expected value of x is greater than or equals to t over 2. So suppose we find such a delta, then what I'm claiming is we can use this expression. Why? Because okay, so y would become x, and what this would say is probability. What this expression would give us is probability x is less than or equals to 1 minus delta times expected value of x is upper bounded by something. And so if 1 minus delta times expected value of x is greater than t over 2, then what we can get is this, right? Okay, so if 1 minus delta times expected value of x is greater than or equals to t over 2, then probability that x is less than t over 2 is definitely upper bounded by the probability that x is less than or equal to 1 minus delta times expected value of x, right? Because if you increase the number over here, this probability can only increase, right? Is this fine?
Yes.
Yeah. So we should find a delta so that 1 minus delta times expected value of x is at least t over 2. Well, this is easy because this double implies, okay, no, because I only have this is an implication, I only have one-sided. Okay, so I want to find such a delta, and what do I know about expected value of x? I know that it is at least something, right? So if I find, or let me write it like this. So I am going to replace expected value of x by its lower bound. So what I've done is I've replaced this quantity by a smaller quantity, which would force this quantity to be larger to satisfy this, right? So basically what the delta that we find over here should also work over here. So suffice is to find such a delta, and to find such a delta, so this implies t and t cancel out, 3 over 4 delta is less than or equals to 1 over 4. Yeah, this is just a simple calculation. Have I done it correctly? Yes. So if delta is at most 1 over 4, then we would have this. So then what we get is this from Chernoff bounds. Probability x is at most t over 2, x is less than t over 2, is less than equals to probability that x is less than or equals to, I'm putting this delta over here, 3 over 4 times expected value of x. This we know from Chernoff, so this is 1 minus 1 over 4, so this we know from Chernoff bounds is at most e to the minus expected value of x over 2 times 1 over 4 the whole square, because delta is 1 over 4. And what is this? This is again so I know a lower bound on expected value of x. So if I put a lower bound on expected value of x, this quantity can only become larger. So we get e to the minus what's the lower bound, 2 over 3 times t times 1 over 2 times 1 over 16, which is like e to the minus order t, which is like 2 to the minus order t. So for instance, if using this expression, you can also find out how large of a t do you want. So suppose you want an inverse exponential error, then t equals to n is just fine. Now, okay, we haven't completely finished the analysis, because we only analyzed this one case, right? When x was in L. We also need to analyze the other case where x is not in L, but that I think it's okay if I don't do that analysis, because that analysis is very similar to this. Basically, again, what you need to do is replace xi is yeah, again it's the same thing. Whatever role 1 plays when x is in L, the exact same role 0 plays when x is not in L. So you can say replace with the probability xi is equal to 0 is at least 1 over 3. That's one, and then carry out the analysis. Or another way is to do it just like this. Probability xi equals to 1 is at most 1 over 3, and then use the second. So we use this bound for the first case. You can use this bound for the second case. So yeah, I won't do the second case. You can try it on your own, and if you have a problem, you can either put it in the forum or ask me in the next session. But are you okay with this first case? Yeah, it was a little calculation heavy, but yeah. Are you okay with the first case?
Yes, this is fine, but like we are only using expectation of xi, right? We are not using like probability of xi equal to one anyway. Like I mean,
Okay,
uh,
so yeah, we are using expectation of xi, but where did that come from?
that is coming from probability of xi equal to one
Right.
and probability of xi equal to zero. But uh,
Okay, so here's the thing. For any 0 1 random variable, the expectation would be exactly the expectation of the variable would be exactly the same as the probability that it is 1, right?
yes, exactly. I mean,
Right.
probability of xi equal to zero will not at all factor
Right.
like uh,
Provided the random variable is 0 1.
provided it is yeah.
Yeah. Because let's say it were 1 minus 1, then the probability that xi equals to minus 1 would better.
Yes, yes,
Yeah.
yes. Okay.
So this was a little
I mean,
calculation.
so
Yeah.
thing is like the same would hold for x not being in L, right? We don't have to repeat the entire calculation again.
Okay, so depends. I mean, so suppose you define xi like this, right?
Right.
Xi is 1 if mx equals to, yeah. Oh yeah, so there is a typo over here. Let xi be the random variable, that is 1 if mx equals to 1, not 0. Yeah. So okay, so right now the way we have defined xi is xi is 1 if mx equals to 1 and xi is 0 if mx equals to 0. If you don't want to repeat the analysis, one way to do it would be as follows. Let xi be the random variable, that is 1 if mx equals to 0 and 0 if mx equals to 1. Then the entire analysis would go through as it is.
Right.
Yeah.
Right.
Yeah,
Yes.
otherwise you can carry out the same thing, but you would have to use this Chernoff bound.
Mhm.
Yeah.
Okay.
Yeah, so let's look at the fourth problem. So suppose we want to boost the probability of success of a PP algorithm, then which of the following is the desired approach? Options are again the same. Run the algorithm multiple times, except if and only if at least one of the iterations leads to accept. Run the algorithm multiple times, except if and only if all the iterations lead to accept. Run the algorithm multiple times, except if and only if an odd number of iterations lead to accept. Run the algorithm multiple times, except if and only if a majority of iterations lead to accept, and there is no clear way to boost the probability of success, at least according to our current knowledge. So which of the following is the correct option, or would you like to guess?
The option E, right? Like
Yeah. Okay. Yeah. So that's
there's
the
no room
correct
for
answer. Yeah.
there's no room for improving our probability of this thing, right?
Right. At least according to our current knowledge. And okay, so we were able to boost the success probability of RP, of co-RP, and of BPP. Why can't we do it for PP? What goes wrong? Like, so what's the intuitive reason why you can't do it for PP? Okay, so if you don't know, the intuitive reason is, if you go back to the definition of PP, there is no gap over here, right? And that's what bothers us when you try to do it. Yeah, so what I'm saying is, if you were to try to work out this entire analysis that we did for BPP, for PP, you would notice that in the analysis, not having a gap is a huge issue. Yeah. So if that's fine, we can move on to the next problem. So suppose that there is a randomized algorithm B which answers accept, reject, or fail, and we are given the following two guarantees. If X is in L, then B always answers accept or fail. Further, the probability that of answering fail is equal to 0.99. When X is not in L, then B always answers reject or fail, and the probability of answering fail is equal to 0.99 again. Then which of the following can we conclude from this statement, and select all the options that apply. The options are L is in ZPP, L is in RP, L is in co-RP, and L is in BPP. So would you like to guess what the answer is, or what the answers are?
I mean, L should not be in ZPP because in ZPP we define the probability of don't know should be less than or equal to half. right?
Okay. Okay. So, okay, how do we
And
define?
not an RP and co-RP, because if in both the cases we know if X is not in L, then we have a probability of X has defined to be 0, and similarly the opposite in co-RP. So it cannot be in RP and co-RP. So probably it is in BPP. I mean,
Okay.
yeah,
So, in the case of RP, we saw how to boost the success probability, right? In the case of co-RP as well as BPP, right?
yes,
So, using the same analysis, you can do the following. Suppose I have defined RP as follows.
okay,
X is in L implies probability mx equals to 1 is 1 over 3. At least 1 over 3. And probability
okay.
and if x is not in L, then probability that mx equals to 1 is 0.
Hmm.
Suppose I have defined RP like this, then is the new definition of RP the same as the old definition of RP?
Yes, right.
Why? Because of boosting, right?
Thing, yes.
Okay, so
Ah,
okay, so let me ask you this again now. Does the 0.99 actually matter? So you said that L is not in ZPP because for ZPP this has to be at most half, right?
yes.
So now I'm asking, does the 0.99 actually matter? Because we saw that half doesn't matter in the definition of RP. It could have been 1 over 3 or in general 1 over polynomial of, like any polynomial of x, size of x. So does the 0.99 actually matter? Okay, let me tell you, it doesn't matter because what we can do is the following. We can run this algorithm B multiple times and do the following. We only output fail if all of the iterations output fail, and if even one iteration outputs accept, we output accept. If at least one of the iterations output reject, we output reject. Okay. If we do this, then using the exact same analysis that we did for RP, we can show that the probability of the new machine output or the new algorithm outputting fail would be 0.99 to the t. So pick an appropriate t. I think about 5 or 6 should do. Then 0.99 would become at most half, right?
Okay.
Yeah, is this fine?
So then our L is in ZPP.
Right.
Right. Okay.
Yeah, so I mean, if you're not convinced, I can work this out. I have some space over here in problem 3. So should we work
No,
this out or is it fine?
one problem that I have is like the previous cases in RP and uh, co-RP and all, like we were boosting in the sense the probability was increasing in the sense like if it was greater than or equal to half, we made it greater than or equal to say two-third or something like an
Right.
increasing way, right? But
Okay.
here it is at most half. Like we are making it. I mean, it would be much better if we say like it is at most one third or at most something like that. But instead, we are relaxing it more.
Okay, uh, so we boosted the success probability of RP, we increased the success probability of RP, but
Yes.
you can also look at that analysis in the following way. We showed that the the probability of failure decreases, right? In fact, if I go back to the analysis that for RP, that's exactly what I did. Okay, so what were we bounding? Probability m prime x equals to 0, and that we showed was at most 1 over 2 to the t,
Oh
right?
yes. Yes.
So
Yes.
we showed that
Yes.
the failure probability decreased, right?
Right. Right.
So I over here, what's the failure probability? It's 0.99, right?
Ah.
Or in other words, the success probability is zero point 0.1, right?
Yes.
Yeah, so I can as well
Zero.
do this. I can do the exact same thing to decrease this failure probability, right? Uh,
Right.
yeah.
Okay. I think I might have to work it out to see it properly. But okay, I kind of get your this thing.
Okay.
Okay.
Yeah. Okay. So if that is fine, then we get LP is in Z, L is in ZPP, right?
Yeah. Yeah.
Then we also get L is in RP and co-RP because ZPP is at the
Yes.
intersection of R is in the intersection of R is the intersection of RP and co-RP, right?
Right, right,
And
right.
RP and
And then
co-RP,
it is
yeah,
in
they are in
BP.
BPP, right? So all of these are
Right.
correct.
Okay.
Yeah, so in general, apart from PP, the constants don't generally matter. As long as in the definition of your complexity class there is a gap between probabilities, constants don't generally matter.
Okay.
Yeah. So the next problem is, suppose that we are given black box access to a univariate polynomial px. So a univariate polynomial is a polynomial in just one variable, something like x square plus 1 or x cube plus x square plus x plus 1. So suppose that we are given black box access to a univariate polynomial px of degree at most d, and are asked to determine if px equals to 0 or not. Describe a randomized algorithm for this problem which succeeds with probability at least half and give its running time. So we are in this question we are asked to like come up with a randomized algorithm for this problem. And what's the problem? I give you black box access to a polynomial. What do I mean by that? You don't actually get to see the polynomial, but you have an oracle access to it. So for example, if I want to evaluate the polynomial at a certain point, I can do it, but I don't get to see what the exact polynomial is. So is the question clear?
Is it something like if I want to evaluate x at 5, the black box will evaluate
Right. So okay.
x
So
at 5 and
right.
right. Okay.
So you give phi to black box, and in 1 second, in 1 unit of time, it spits out p of 5. So you don't need to worry about how
Right.
much time black box takes.
Okay. Yeah.
Yeah, that's the input model. Okay. So then, if the question is clear, would you like to guess what the algorithm is, or would you like to like propose something?
Well, I have an algorithm, but I don't know whether it succeeds this
Okay.
thing. So I'll just so randomized algorithm we want. So
Right.
that means we randomly choose some value for x
Hmm.
and give it to the black box, and
Right.
if it returns 0, then you accept
Okay. Right. Then you say
you
the polynomial is 0. Right.
0, right? Otherwise, you say polynomial is not this thing.
Okay.
It's not identically 0.
Right.
Yeah.
Yeah. So you have the outline correct. That's exactly what we are going. What the algorithm is going to be. But there is just one technical issue, right? So yeah, we aren't told about what field we are working on. So we'll suppose that x can take any real value. Okay.
Right.
Now what does
Yes.
it mean to say that you are going to pick a random real number? For example, like picking a random bit is simple, right? 0 with probability half, 1 with probability half. But there are like
Yes.
infinitely, like uncountably many real numbers. So what does it mean
Yes.
to say that you pick a random real number?
Okay.
Okay, one very simple way to do it is this. Like take any reasonable distribution over reals, for example, the normal distribution or the Gaussian distribution, and work with it, right? But there
Yeah.
is also another issue with this. How do you write down a real number? How do you give the real number to the black box? Because a real number might as well be irrational, right? For example, the real number you picked was pi. How are you going to give pi to
Right.
the black box? You can only do it up to like certain like decimal points, right?
Yeah. Certain. Yeah.
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 So we
Certain
can,
approximation.
huh?
Certain approximation.
Right.
Yes.
Yes. There is a very easy way to get around all of this, and it's the following. The basic algorithm is exactly what you suggested. So here's the algorithm. Pick a number A uniformly at random from the set 1, 2 up to 2 to the d. Output 0 if pa equals 0 and non-zero otherwise. This is exactly the algorithm you suggested, except that I am now saying that a is not going to be a random real number, it's going to be a random number from this set. Okay. I think
Right.
someone wants to join. Yeah. Okay, so now let's see why this succeeds. So let's first analyze the case when px equals to 0. Now if px equals to 0, no matter which number you pick from 1, 2 or 2 to the d, or for that matter which real number you pick, pa is always going to be 0, right?
Yeah.
Yeah.
Yes.
So if x equals to 0, p is always going to be 0, and so the algorithm is always going to output 0.
Right.
Yeah. So if x equals to px equals to 0, it works with, like, there is no probability of success. It works 100% of the time. But if px is not equals to 0, then we need to do something, right? Okay. So what we are going to do is the following. Now px is not equal to 0. We know that the degree of px is at most d. That is given in the question. So we'll use the fact that a degree d polynomial, or a polynomial of degree at most d, can have at most d roots. So are all of you familiar with this fact?
Yes. Yes.
Yeah. Okay, so what does this say? This says that there are at most d real numbers, so that p evaluated at the real number is 0, right? In particular, there are at most d real numbers in this set, so that p of a equals to 0. Is this fine?
Yes.
Right. So if you pick a number uniformly at random from this set, what's the probability that the number you picked is such that p equals to 0? It is at most half, right?
Right. Yes.
Yeah. So there's for at least half of the numbers in this set, and therefore with probability at least half, the PA would not be equal to 0, and so the algorithm would output non-zero, right?
Right.
So the success probability in this direction is at least half.
Right. Yes.
Yeah. And what's the running time? The running time is exactly the amount of time it takes you to pick a number from this set. And one way to do it is the following. Just write down the binary expansion and pick every bit independently random. Yeah, and like for 2D, the number of bits required to write its binary expansion is like ceiling of log 2D. So that's order log 2D, which is order log D. So the running time is order log D, assuming that the black box evaluation takes unit time.
Right.
The running time is order log D plus whatever time the black box requires. Yeah. So is this algorithm fine? Because the next question is going to be based on this. Okay.
I mean, the set 1, 2 up to 2D should not matter. Right?
Arbitrary.
In fact,
Yeah.
you can take any. Yeah.
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 Just take a set of, just to be to avoid the problems with irrational numbers, take a set of 2D rational numbers. Any 2D rational numbers would work.
Right.
In fact, this problem there is a reason I included this problem. It's called the PIT, or the polynomial identity testing problem.
Yeah.
And for univariate polynomials, we'll see in the next question that you can even come up with a deterministic algorithm.
Okay.
But for multivariate polynomials in more than let's say n variables, right now we don't know of any deterministic algorithm that works in polynomial time. But we do know of basically this algorithm of randomly picking numbers also works in that case. We won't cover it over here, but that's called the Schwarz-Apfel lemma in case you want to look it up. Yeah. Okay. So describe a deterministic poly D time algorithm for the previous problem. So we saw a random algorithm. Now what I'm saying is try to make that random algorithm deterministic. So how do you do that? How would you do that? So here's the algorithm. How would you make this algorithm deterministic? Okay, so what is the algorithm doing? It's picking a number uniformly at random from 1 to 2 to the D, right?
Instead of uniformly at random, we go one by one.
Right. One by one, check everything.
Yeah.
There's a 2D number, so order log D. Sorry, order D time, right?
Right.
That's exactly the algorithm. Evaluate PA for all A in 1 to D plus 1, output 0 if all evaluations are 0 and non-zero otherwise. Why D plus 1? Well, there are at most D roots, right? So D plus 1 is fine by Page's principle. One of them has to be a non-root.
Yes.
Right, so we don't even need 2D. The only reason we needed 2D over there was because we wanted the success probability to be at least half.
Yes. Yes.
Yeah. And yeah, so the running time of this is order D, because D we are going to run a loop from 1 to D plus 1. Yeah. So so this was all that I had for like a randomized computation. Now let's look at some Problems related to circuit complexity. Okay. So suppose we need to build the function and n from 0 comma 1 to the n to 0 comma 1, which is the end of all n of its input bits. To build this, we have AND gates of fan in 2, that is AND subscript 2, OR gates of fan in 2, OR subscript 2 gates, and NOT gates. So what is the size of the smallest circuit that implements AND subscript n using AND 2, OR 2 and NOT gates? The options are 2, log n, n over 2, n minus 1 and n. So would you like to guess what the answer is?
For this one, I don't know whether it is the smallest, but I know this using the De Morgan's law. Like we have like x1 and x2 is equal to so x1 bar or x2 bar the whole bar, right?
Yeah.
So we can try to apply that formula, but I don't know whether that should be the smallest circuit.
Okay. Okay, so the question is not asking the smallest circuit, it's sort of asking smallest among these. Yeah, because proving,
smallest among
proving
these,
it
okay.
smallest might be difficult.
Okay. So then using the De Morgan's law, I got that D is equal to n minus 1 thing.
Okay. There, D equals to n minus 1 is the answer, but I don't see why we need De Morgan's law. Okay, let me show you why we don't need De Morgan's law.
Sure, okay.
Yeah, suppose n equals to 3. What would your circuit be? Okay, let me start with n equals to 2. That's the Vx case. So if n equals to 2, here's the circuit, right? AND gate, x1, x2. Because we have 2 input AND gate, right?
Yeah.
So n equals to 2 is the simplest case. What about n equals to 3? So n equals to 3, you are supposed to evaluate x1 and x2 and x3, right? This is the same as x1 and x2 and x3. This is the same as y and x3, where y is defined as x1 and x2, right? So does this suggest a circuit for n equals 3?
Oh yes, okay.
Yeah.
Okay.
And another and, okay, so x3 over here, x1 over here, and x2 over here. N equals to 3, we need 2 gates, right? Similarly, we can do this for anything, right?
Yes.
So for any general n, this is just what a circuit would look like. I can start it from here. AND gate, x1, AND gate, x2, again an AND gate, x3, so on, and the last AND gate would be xn and xn minus 1. Yeah, and we are only using n minus 1 gates. Why? Because each AND gate except the last one takes as input a fresh variable, right? The last one takes 2 fresh variables. So 2 variables from here and n minus 2 from here. Okay, so these 2 variables pay for this one gate. These n minus 2 variables pay for another n minus 2 gates. So we only have n minus 1 gates, right?
Right.
Yeah. So you can probably do this using De Morgan's law as well, but yeah, this is a very simple way to do it.
Yes.
Yeah. Okay, but this does not answer the question, right? This just shows that n minus 1 is a possibility. Like you can construct a circuit of size n minus 1. What about these 3 numbers? Well, okay, first of all, you need to at least read the entire input, right?
So 2 should not.
Yeah, 2 will only let you read like what? At most 4 bits of input?
Yeah.
What about log n? It would let you read 2 log n bits of input, right? So 2 and log n are out of the question directly, right?
Yes.
Because they don't, using 2 and log n, 2 or log n gates, you can't even read the entire input. What about n over 2? Using n over 2 gates, you can read the entire input, but then you can't do anything else. You can't sort of combine the information that you have obtained from different gates, right? So what I'm saying is, for 2 and log n, I can give a very simple proof why it won't work. You can't read the entire input, but for option C, I'm not giving you a proof. I'm just giving you an argument that why it won't work.
And what is that? Like n by 2, what is that argument?
Okay, so you have n over 2 AND gates, right? How many bits can you read using these gates? Each gate can read 2 bits. In the best case, all of these bits can be distinct. So 2 times n over 2, that is n bits, right?
Right.
So you have read all the n bits, but can you do anything else? Like, can you combine the information that you obtain from these n gates? Sorry, these n over 2 gates. What I'm saying is, you have x1 and what you have what x1 and x2 is, what x3 and x4 is, and so on, right?
Yes.
But can you combine this information to say something about x1 to xn?
No.
Right, because you have used up all your gates, right? Now, I agree, this is not a proof, but this is an argument why n over 2 won't work, right?
Yeah, this is one way why. Okay, this is one
Yeah.
approach. There
Right.
could be something else.
Right, but no matter what you do, either you can't combine all the information, or you can't read the entire input, in which case, yeah, you have a problem.
N by 2 should be.
Right.
Yeah. So right now we have shown that n minus 1 is the best possible that we could come up now. Right. I mean, there could be something more smaller also if possible. Has the lower bound been shown? N minus 1 is the smallest.
I don't know if we know lower bound on the circuit size, but yeah, I think some similar lower bounds are known for something called communication complexity. I think they might imply something over here.
Okay.
Yeah, I'm not sure if there is a simple proof showing that n minus 1 AND gates are required. Yeah. Okay, so the next problem is, the depth of a circuit is the length of the longest path from the output gate to any input, okay? And suppose we have a circuit C that uses AND gates of fan-in K, OR gates of fan-in K, and NOT gates to implement a function. Suppose C has depth D, and suppose we want to construct a circuit C prime that is equivalent to C, but you only using AND gates with fan-in 2, OR gates with fan-in 2, and NOT gates. So from the given information, what is the tightest upper bound on the depth of C prime? So is the question clear?
Well, okay, so C is using AND and OR gates,
but of a larger fan.
For larger fan,
Right.
So that means, so possibly we can use the problem 8 or something to.
Okay, problem 8, the idea is similar, but problem 8 gave you an upper bound on the size, right? Here you want an upper bound on the depth.
Right. Yeah. Here we need on the depth.
Yeah, but the idea is similar. Okay, so let me tell you, the answer is B, D times ceiling log K, and the reason is the following. So, okay, I'm just going to show you for OR gates. This construction for AND gates is similar. So the goal is this. An OR gate of fan-in K using OR 2 gates. So OR gates of fan-in 2. Okay. Let me just write this a little more neatly. And we want to do this while keeping the depth of the circuit minimum. So here's the construction. let there be an OR gate at, okay, so let me first write down a formula, then I can construct it. So we want this. For the sake of simplicity, I'll assume that k is a multiple of 2. That would make my life easier. This is x1 or x2 or xk over 2 or xk over 2 plus 1 or up to xk. And if, okay, let me assume k is a multiple of, not a multiple of 2, but a power of 2, in which case I can sort of open, like, write similar formulas for both of these parts, right? So is this formula fine?
Yes.
Yeah.
I mean, x1 or x2 or x3 or x4. For that, we can have x1, x2, x3, x4, and then combine.
Right.
Right. Okay.
Yes. And does this suggest a formula for this, or a circuit for the implementing this OR gate of fan in K using just OR gates of fan in 2? Okay, so here is the topmost OR gate. So the middle OR gate in this formula is the topmost OR gate, and in the left and right I want to compute these two, right? But these two are exactly the same as this, except that the number has gone down, right? So what I can do is I can just keep on repeating this. And at the very bottom I can have something like this: x1, x2, x3, x4, xk minus 1, xk. So I am assuming k is a power of 2, so I can create a binary, complete binary tree of OR gates, but the leaves of the tree are x1 to xk. So the claim is this would compute. The claim is that this would compute x1 or x2 or xk. So is this claim fine with you? So for example, if k were just 4, this would be just this with x1 over here, x2 over here, x3 over here, x4 over here. So is this claim fine?
Yes.
Right. So okay, now what is the depth of this tree? It's a complete binary tree,
yeah,
of with k leaves. So the depth is log k, assuming k is a power of 2. Okay, so we have figured out how to implement an OR gate using like smaller OR gates of fan into if k is a multiple of 2, or sorry, k is a power of 2, right? What do you do if k is not a power of 2? Well, observe that if I replace xk by okay, so what I'll do is the following: if k is not a power of 2, I'll look at the next largest power of 2, which would be at most 2k. It can't be more than 2k. Let me call that number k prime. Then what I'll do is I'll replace all the numbers, sorry, all the inputs xk plus 1 to xk prime. I would put all of them as 1, and the OR would still not change, right? So the resulting OR would exactly be the OR of x1 to xk, right?
Yes. Yes.
Yes. So then I would construct this circuit with k equals to k prime.
0 or 1. OR gates, so 0.
Oh sorry, oh yeah, sorry, OR gates are 0, right? Yeah, and gates 1, right? Yeah, thanks.
Okay.
So yeah, we can replace xk plus 1 to, we can construct this circuit, replace xk plus 1 to x k prime by 0, and what would the depth of this be? It would be like ceiling of log k, right?
I mean, or log k, because you are replacing by 0.
Okay, then you want to remove these gates. No, yeah, you can do that. What I was saying is, you keep this entire thing, doesn't matter, with zeros and everything. It would still be at most like ceiling log k, right?
Right. Okay.
Yeah, and you can do this for every gate, every AND or gate which has a larger fan in, right?
Yes.
So basically, in the original circuit, that gate would contribute only 1 to the depth. Now it is contributing ceiling log k to the depth. So the blow up is like a factor of ceiling log k. So the answer is d times log.
Right.
Because
Yeah.
in the worst case, you can have like a one very long path with just AND gates of tan n k, right?
Mhm.
Yeah. The answer is d log k. So that's all the problems we had for today. So if you have
Yeah.
some questions, you can ask. Otherwise, we'll meet next time.
Uh, I don't have any questions actually.
Yeah. So in that case,
This is
we
fine.
can. Oh wait, is there something in the chat? Oh no. Yeah. So in that case, we can just meet next time. Next Saturday from 4 to 5 the same time. Okay. Yeah.
Thank you.
Yeah. See you.
Thank you, brother.
Bye.